optics, there are a whole slew of things that will become interesting to us. But what we really need to start with in the world of optics, which is, kind of looking at light, we're pretty much looking at light here, is there is a ray model of optics and there is a wave model of optics. We right now are going to focus on a ray model. Okay, that's what we're going to focus on to begin here. We'll come back to this later on, but for right now, who cares? Okay, and when we're talking about this ray optics or geometric optics, we're really talking about how light kind of bounces off of surfaces. Okay, so imagine for a second that right here, pretend this is like a mirror for us. Okay, so we've got a mirror here, and oh, that's why it went weird, because Noah's trying to get in. There he is. So we've got a mirror here, and if this mirror, we got to have a front and the back of the mirror. Okay, so let's call this is like the back side of the mirror. We've like put it on a wall. And this is a plane mirror because it's just vertical. It's not curved at all. It's not weird. It's just a flat mirror. This is something you see in your bathroom, right? You're brushing your teeth. You're looking at yourself. You're like, man, Leo's going to say I look great today, even though I know I look like garbage. And for a plane mirror, if you're standing here, here's you. I don't know what size your torso is compared to your head, but it exists. When you strike this mirror, when a ray of light, so like a ray of light, comes from a light, it hits your head, that ray of light could reflect off of it, and when it strikes the mirror, it's going to bounce off of this mirror here, like this. And in theory, another ray of light could hit your head at the same spot, reflect differently, and maybe it reflects like this. Okay? Notice right now that these two rays of light, if I were to extend them out to infinity, they are never going to hit one another, right? One of these is kind of going like this, and the other one is going like this. They're never going to hit one another in this direction. We say that these rays of light are diverging, or that they diverge. So these two rays of light are divergent rays. They're never going to strike one another. Now, if this is the case, how do you actually see yourself in the mirror? Like, there's a man in the mirror. How do you see that person? So what we actually can do with light, and this is a little bit weird, and we'll talk about this in more detail as we go on, but if you were to draw this light where it could have come from, this is what you'd see. You'd see the man in the mirror. Your eyes don't actually understand what bouncing light is. They don't understand what a reflection is. Like, if you toss a ball off the wall and it kind of like ricochets, your eyes don't understand what that is with light. Your eyes believe that this light only can move in a straight path. Your eyes believe that the light started from behind the mirror and came out of the mirror. That's what your eyes believe. That's not what's happening, but your eyes are on a giant meat body. We're kind of stupid, even though we're really smart. We just, don't have a good idea of what's going on here. So there is no light back here. There's no light back here at all, but your eyes thinks there are. Okay, and that's because these rays are divergent here. Now, since these rays technically on the back end, they're not there, but they would still hit. When these rays overlap, we call these converging rays. Okay, so these rays are converging right there, while these rays out here are diverging. And that's the first thing we care about there. Okay, and that's just so that, if you had an eyeball out here, whoop, here's my eyeball, we would think that, it looks like a person is back here, but in reality, They're over here. Okay? That's why like houses of mirrors and mazes like that, they work so well and they confuse little children and they run into walls and it's hilarious because of this effect. Now, within the world of optics, there's two laws of reflection that we always have to obey in looking at this. The first is that the two rays and the normal they are in the same plane as the normal. Now, that's like a really, really weird thing, but imagine this. Imagine you had a mirror in front of you. Let's look at this with a sheet of paper. If I had a ray coming down like this, it's going to hit this paper, and then it's going to bounce up like this, right? Or if this was a mirror, it would bounce, and then it'd bounce out. I couldn't have a ray bounce down like this, and then all of a sudden come like that. That doesn't make any sense, right? Like, that's what this first law is talking about. It doesn't make sense that you're like tossing, imagine a hockey puck, moving across the ice and it bumps into the wall. Like, the hockey puck wouldn't do one of these. It wouldn't be like, oh, look, here comes the hockey puck. And then all of a sudden, you would imagine it should bounce like that. Imagine all of a sudden it, like, moves into the ice or out of the surface of the ice. Like, that just doesn't make any sense. You just can't all of a sudden have a random turn for no reason. So that's what the first law is saying. No rando turns. Okay? You can have a turn, you have to angle things in the line of the normal. Our second law here is actually what I've drawn down here. If we take a look at this mirror surface, the line normal is here. This is the normal line. It is the line that is perpendicular to our reflective surface. If I have a ray of light come in, let me draw this better. If I have a ray of light come in, whatever angle is made here, this is theta I. It's the angle of incidence. That angle of incidence must be the exact same as this angle here. This is theta R. This is the angle of reflection. And we know that angle of incidence must equal the angle of reflection. Okay? That is a law. That is our second law right there. So the first law, you just can't randomly turn. It doesn't make any sense. Like, you've seen that. Like, it doesn't happen. And the second law is just things should kind of ricochet or bounce like you would imagine they would bounce. And what you've seen your entire life, this angle of incidence measured from the normal is equal to the angle of reflection measured from the normal as well. Okay? So those are our two straight up laws there. Now, if we look at things that have light bouncing off them, we have two different ways things can look. They can look diffuse, or diffuse reflections, or they could look specular. In diffuse reflection, light scatters everywhere. And in specular reflection, we kind of get a mirrored surface, or things look shiny. And what I mean is this. In a specular reflection, all of your light rays, as they come down, they reflect, and the angle of incidence has to be angle of reflection, and we get this. All the parallel light rays come in, they all strike, and they come out the exact same. Okay? That's what happens. We kind of get some mirroring that occurs here because, we see that the red is on the downside here on the far right, but that's what's going on with a specular reflection. Things look shiny. Anytime you're looking at a sheet of metal, or a spoon, or like a glossy surface, that's a specular reflection. Okay? And the reason why this occurs is because on these like normally metallic surfaces or kind of shiny surfaces or glossy surfaces, there is very little bumps on a microscopic level. They are very smooth. They're very, very smooth. Most of the things that we see are diffuse reflections. If you're taking a look at my shirt, or maybe your shirt, unless you're wearing like plate armor for some reason. If you're taking a look at the Bucky koozie I have sitting around here, or a sheet of paper, none of these look shiny. And the reason being is on a microscopic level, they're actually really rough. They kind of look mountainous. And what happens here is, as some of the light comes down, it might hit this and reflect this way. And as some of the light comes down, it might hit this here and bounce this way. And as some of the light comes down, maybe it's going, maybe it does this. The light kind of goes in all directions. And because that light isn't staying together, we get some really weird things happening. We don't get a nice mirroring of the surface. It doesn't have a shine to it. We really don't get a good image out of it. If there was another ray of light that passed in right about here instead, it would actually kind of reflect off and do that. So the image kind of gets like mashed together, and you don't see a nice mirroring of the image. You just kind of see that the shape exists. This is a Bucky koozie. I don't see myself in it. It's there. Okay? So this is a diffuse reflection. Okay, so that's the difference between a specular reflection and a diffuse reflection. Now, when we start actually looking at mathematical problems for this, we're going to have some variables that we're going to need. And one of the most important variables is the image distance and the object distance. Now, depending on how old you are, who taught you, what book you used, and whether or not you took the AP test, you might use a completely different variable for these two things. Some people use for the object and image distance P and Q, because that makes sense. We're not going to use that because honestly, I can't even remember it. What we're going to use is we're going to use DO for object and DI for image. Yay. However, while some books use that, some other books and the College Board may use SI and SO. They all mean the same thing. One of these is just an image distance. One of them is the object distance. And in both cases, it's just how far away is the image or the object from the mirror or the lens. And we'll talk about lenses later on, but for right now, we're just sticking to mirrors. Okay? So if you've got a mirror here, and here is you are the object, DO. Your image on the back side of the mirror, this is DI for the image. Okay? So the object is the physical thing that you're reflecting. The image is what is being created through your rays of light. Okay? In the case of a plane mirror, so a flat mirror like this, for a plane mirror, it can be shown that the object distance will equal the image distance. Okay? They will be the exact same there, which is kind of a neat thing. Hopefully we'll be able to show that with the man in the mirror. And the last thing we have to talk about, just in terms of a general introduction and whatnot, is this idea. Virtual images. So there's two types of images that we can actually create. We can create a virtual image, or we can create a real image. Now, a virtual image, when the light rays, when they reflect, or when they pass through a lens, they're not actually going to converge, okay? The light rays don't pass through the image. You cannot project it. And what I mean by that is you essentially have diverging rays. You have diverging rays there. For a real image, the light rays are actually going to pass through the image point, and it can be projected. These are converging rays. Okay? And as Job would say, it's an illusion, Michael. Now let's see if I can bring up Mr. Frog. Where would I have put him? I don't know if this is going to work. virtually like this. I'm gonna be honest, I don't know if this is gonna work. So we're gonna see. We're gonna see if this works. Oh, you know what? I think it is. Haha. So do you see that? Where is it? Yeah, it's weird because I'm trying to get it to. Okay, there. Yeah, do you guys see my frog? Hold on. Work with me. It's weird because I'm trying to do this like backwards in my camera. You guys see that frog? Yeah. So that frog that you're seeing doesn't actually exist. You see that? Like, see, he's down there. But the frog that you're seeing isn't that one. You're actually seeing a real image of him. Let me turn him this way. Let's see if I can get him to look like this. Oh, come on. Yeah, the thing is, when I tip him, he slides forward. Yeah, so do you see that? Do you see that frog there? Like, that frog is a real image. Like, he's not actually there. He's down there. But this light is actually converging at this image point. And, you know, if we ever get back into the building, like, this looks so much cooler in person. When you put this down on the table, like, you see an actual, like, it's like a 3D frog is in front of you. It's like wild. Let's see if I can. Oh, let's try this. Let's try this real quick. Let's get cam 3 going. Let's see if I can do this with cam 3. Oh yeah. Do you see that? Do you see the frog? Okay, see that frog there? See, it's not. Like, it's not a real frog. It's just a light. It's just an image. Like, I can put my hand through it. Do you see that? My hand's like through the frog. So it's not actually a hologram. A hologram is actually something a little bit different. This is what is just referred to as a real image. The light rays are actually doing something cool here. The inside of this is 2 mirrors. The frog is actually lights coming through the top. It's striking the frog. It then bounces up, hits the top mirror, and then the top mirror bounces light down on the bottom mirror, and then this light refocuses everything so that it comes back through the center, and you actually see the frog. And you can do this with all sorts of stuff. Let me try to find. I don't have anything. Oh, maybe something in my desk. Do I have a quarter or something? Yeah. So that's silver. I don't want that. Will this spring work? Here, I've got like a little spring here. See? Just a little spring. Probably giving someone out there motion sickness. Apologize. So like, that spring's not doing anything for me. Let's see. Maybe this penny will work. Okay, so there's just a penny there. Good old Abe. And like, there's the penny up top. Like, my finger's through the penny now. Isn't that wild? So that's what a real image is. The image, like the object isn't actually there. It's just an image of that object is. And this is very different from a virtual image, because a virtual image, you actually won't, my screen on my screen. You actually won't see a virtual image. a virtual image is only there in your eyes. And the reason it's only there in your eyes is because your brain is pulling tricks on you. When you see a virtual image, you see it, but it's not physically there. Seeing yourself in a bathroom is in like a plane mirror. That's a virtual image. So yeah, a real image is something that can be projected. You can throw it onto a screen. You can watch it at a movie theater. Those are real images. Virtual images are things that you cannot project out, and you only see them as a human because your eyes are playing tricks on you. So kind of a weird thing, but that is what is going on in terms of virtual images and real images. So that's what we're seeing thus far. We've got the idea of a virtual image, we've got the idea of a real image, we've got plane mirrors, we've got object and image distances, diffuse reflection, specular reflection, and then our laws of reflection here. You can see up here for the plane mirror, this is a virtual image. There's no light back here, but that's still where we think the object is from. That's going to make a virtual image. So that's what's going on to start this off. Okay. We're going to see next, and I'm going to have to pause things for a second here. We're going to see next here is this idea of the man in the mirror. How do we look at a plane mirror, and what's going on with that?